Hi everyone, this is Laura from Mithril Security, and today I'm talking about our new confidential AI assistant BlindChat. So in our previous video, we gave you a quick tour of BlindChat, we saw what it looks like, and we saw how it keeps user prompts private so that not even our admins can access user data. In this video, we're going to dive deeper into the technology that underpins BlindChat and that we believe can be crucial for building safer AI, namely a secure and verifiable computing environment called an enclave. Enclaves are at the heart of all of our confidential AI solutions, and they help us to address these two key technical problems in the industry: data confidentiality and code integrity. So with regular AI, data sent to an AI application is exposed to the AI provider in clear, which means that it could be misused, it could be used to train models on, or it could even be leaked if the company were to be breached. We also have no way to verify that a server that we send our data to is actually running the expected code or model. So enclaves help us to resolve both of these issues. They bring confidentiality and they bring verifiability. So data analyzed in an enclave is not exposed even to the party that manages the enclave, thanks to isolation and encryption. And they also provide cryptographic guarantees that an enclave with the right code and security features is actually being used by the service provider. So we've discussed what enclaves are and their potential for protecting user data. So let's now have a look at how they work, starting with how they ensure data remains confidential even from the rest of the system. So users' data, when it's sent to an enclave application, it's encrypted, and it's only going to be decrypted once it arrives inside of that enclave. And remember, this enclave, it's shielding its content from the rest of the system. So effectively what that means is that an admin on that system, a member of staff, even a malicious actor, a hacker who's got access to that system, they still have no way of getting to the contents of this enclave. And while the type of encryption used can vary depending on the specific enclave and enclave provider, the general idea is these keys are going to be created in protected memory, often inside of the enclave itself, and that means that no one is going to be able to access these encryption keys. So at this point, the AI providers deployed their application inside of this inaccessible, shielded environment, and they can't see any of its contents or processes. But that leads us to another problem, which is how can we actually be sure that the enclave is correctly configured and it's actually running the correct application, the correct code, and it hasn't been tampered with. So this is where attestation comes in. So attestation is a process that gives us cryptographic proofs that we're actually communicating with an enclave with the right code. So it can be seen a bit like a checksum for applications, but running in these trusted environments. So when users attempt to establish communications with an enclave, they can request what we call an attestation quote or an attestation certificate report, and this contains cryptographic proof of the enclave's identity. And that's signed by a key which is derived from a trusted party. So that could be the hardware provider, the cloud provider. But basically this attests that a specific code base has been launched within the enclave. So this means that we can then verify that proof. We can check that it matches against expected hash values that we have relating to this specific code base or enclave. And that means that we can actually take this cryptographic proof, we can check that it matches the expected hash values that we have for our code base or for the enclave. And that means if something doesn't match up, if there's been a modification to the code that we weren't expecting, if we're not actually talking to an enclave at all, we can see that early on in the communication process, and we can cut that, we can stop that communication before we ever send any confidential data to that service. So thanks to attestation, end users have this proof that an enclave server is genuine and it's loaded with the expected code. But then how can we be sure that they're communicating with an enclave and they're not merely being forwarded this genuine proof from a man in the middle who's intercepting these enclave reports and just forwarding them onto the end user? So we need to be able to kind of check the ID of the server that we're talking to and check that it matches the ID of the enclave. And we're able to do this with attested TLS. So with attested TLS, when an end user first attempts to connect with an enclave, they're going to receive a TLS certificate and a signed attestation quote or report. And this signed attestation quote is going to include a hash of the enclave's TLS certificate. So firstly, when we verify the attestation quote, we're going to be able to check that the enclave has the expected TLS certificate hash in their report. So we can check that matches against an expected value that we have for this service. But then we can then check that this value this hash TLS certificate value matches also with the TLS certificate that we've been sent by the enclave before we start any communications using this TLS certificate. So it's worth noting that the associated private TLS key is born, lives and dies inside of the enclave, which means that no malicious actor is going to be able to get hold of these keys. So at this point, we now have a solution which is offering confidentiality, code integrity, and it's really guaranteeing that we're really communicating with this secure service. So all in all, this makes this really powerful combination that can be used to secure applications. So now let's have a look at some of the different enclaves available today. So as you can see, there are lots of different enclave providers, and their enclaves come with different trade-offs. We have some solutions like Intel SGX's secure enclaves, which are hardware-based and protect a single application. And then on the other end, we have Intel's TDX enclaves, which are virtualization-based and can protect and verify a whole VM. So which enclave was the best fit for BlindChat? Well, we didn't actually use any of the enclaves which you can see on screen now, and that is because none of them support the use of GPUs, which was critical for us in order to reach good performance for LLM inference tasks. So what we did instead is we decided to build our own type of enclave using Virtual Trusted Platform Modules, or TPMs. So TPMs are a tried and tested technology that can be used to measure, store and verify the whole software stack of a machine. So with our enclaves, we ensure confidentiality through the deployment of a container with strict isolation policies, as well as a custom minimal OS, which is loaded in RAM to avoid attacks on disk. We then ensure integrity through TPM-based attestation, which verifies the custom OS, the application, and the TLS certificate of our enclave. So I know I've thrown a whole lot of information at you there, but I hope that you now have a better understanding of how enclaves work and how they can be used to create secure AI applications. We'd really love for you to go out and test BlindChat, see what you think, and let us know on Discord or by email, or even by setting up a call with us. So thanks for watching, and I hope to see you again soon.